Having just finished talking about rank, let's jump into homogeneous systems. So a system is said to be homogeneous if all of its constant terms are zero. So here is our kind of traditional example, the example that we've been carrying through, except again, notice that all of the constant terms here are zero. Okay, so given any linear system, we might also talk about its associated homogeneous system, which is the homogeneous system we would get if we made all the constant terms zero. That is, we keep all the coefficients the same. Now, the following theorem tells us how to relate rank with the number of parameters of a solution set. So if we have an m by n matrix A, and this is the coefficient matrix of a linear homogeneous system, and the rank of A is R, then there are n minus r basic solutions. Namely, there's a basic solution for each parameter. And the number n minus r makes sense since it denotes the number of columns without a leading one. Okay, moreover, every solution to the linear homogeneous system is a linear combination of the basic solutions, and we'll see in a second that this is quite natural based off of how we extract the basic solutions. So to illustrate this, let's do an example. Let's find the basic solutions to the following linear system. And note again that this is homogeneous since all of its constant terms are zero. And let's write down the augmented matrix and row reduce it per usual. And for homogeneous systems though, the augmented part isn't very useful. If you think about our three elementary row operations, you'll see that no matter what we do, the constant term will always stay zero. Anyway, so row reducing this gives us the following. Now, there are n equals 4 columns, and that's 1 for each variable, and the rank of the system is 2, so there should be 4 minus 2 equals 4 basic solutions. And this, again, corresponds to 1 for each parameter, and we'll see why that's true in a second. So let's solve this system like we normally would. We're going to write out our new simplified system that's given by the RREF form. And if we isolate for x1 and x3 and rewrite our solutions in terms of the parameters, we get this. Now we're going to have to write out the full solution set as so, and this is going to help us see how to extract our basic solutions. And to do that, let's split this into vectors based off of our parameters, so one for s and one for t. And if we factor out the s and the t, we get this. Now the two remaining vectors here are our basic solutions, and note that by virtue of what we did, all solutions are a linear combination of these two vectors. So why do we care about homogeneous solutions? Well, it turns out that homogeneous solutions are part of even the non-homogeneous solution set. Let's write this as a theorem to show you what I mean. Every solution of a linear system is going to be of the form xp plus xh, and here xp is a particular solution, and xh is a homogeneous solution. So to show you what I mean by this, let's do an example. So let's find all the solutions to this linear system. Now this is just the linear system that I wrote above, but I'm writing it straight in matrix form because I don't want to rewrite the whole thing again. But if we row reduce this per usual, the RREF of the coefficient matrix will be the same, right? Like that's not going to change. But of course the constants will be different, so you should go through it. Like before, let x2 be s, let x4 be t, and let's rearrange for x1 and x3 so we can solve for them. And if you look closely, you'll see that the homogeneous system appears, and I've underlined it in red. Okay, so let's write out everything full again, and if we do that, we get this. And once again, we're going to split this into vectors based on each parameter, but this time we're also going to pull out the parts that don't have a parameter. And this gives us 3 vectors, 2 with a parameter, 1 without. The vector without a parameter, that's our particular solution, while we see that this thing here, this is our homogeneous solution that we had before. So with these results about rank and homogeneous systems, we can now solve any system with infinitely many solutions.